as you notice in the program, my talk was entitled TBA, and of course it's not due to my disorganization in not sending a title. It's of course due to the fact that TBA stands for Taking Back Their Approximations. Actually, the talk was TBA because basically lately I started being a little bit less optimistic about doing inference and what's all involved about doing inference. So what I decided to talk about is snakes and ladders. So I'm sure you know about the game Snakes and Ladders. It's a very old game. It started in India many centuries ago. And this is an example from last century. And when I talk about concordant cosmologies and all that, two things come to mind. One is this game, and another one is this fresco. I don't know if you recognize it. This is the Vasari fresco from Florence Duomo. And the nice thing is that up here there is concordance, everybody's happy, we have all these grandiose ideas. But down here there are strange snakes lurking. And so coming back to these kind of things, there are things like ladders that brings you up towards concordance and all this wonderful connection between cosmology and fundamental physics. And then there are things like snakes that brings you down and you hit things like that. So this is the theme underlying my talk. So let's get going. So why am I not that optimistic? Let's just say that. Cosmology, it's special because we don't make experiments despite the fact that we sell them to the funding agency as experiment. We only make observations. So the universe is given as it is, and we can't change the point of view. We can't change it. We have to use the entire universe as a detector, but the detector is given, so we can't tinker with it as you would do with any other experiment. So this has given a massive experimental effort that is, well, the bigger the detector, the better we can do, so observe as much as possible of the universe. And this has also other consequences, but I'll discuss this later. This is a missed blessing, which is in part the course of cosmology, because we only have one observable universe. Since we have only one observable universe, we only make observation. Only of the observable universe, and then we want to make inference about everything and not just the observable universe. And also we have to fit models, that is, constrain and tune numerical values of parameters of a model to observations. And therefore, almost any statement that we do in cosmology ends up being heavily model dependent. And then on top of that, there are nonlinearities and gastrophysics that ends in and make the entire game a little bit more complicated than it would appear a priori. But this is also the blessing because we can observe all there is to see. We almost do. And this introduced the concept of what I call the ultimate survey. Once you observe all there is to see, there's no point of repeating the experiment because, well, you've seen everything. And actually, in the future, the next generation surveys will be ultimate survey. And I should just say that actually the future is here because Planck, which some of you are part of, is an ultimate survey because for the primary temperature fluctuation, the information content has been saturated. That's all there is to see. So if you were to repeat the experiment, you would have to go after other things that are not the statistic of the primary temperature fluctuations. So the primary CMB temperature fluctuation content has been saturated. The near future now turns to larger scale structure. I am not saying that the game has ended for the cosmic microwave background. I'm not saying that. I'm saying that there is another game there, which is full polarization, and we have learned from the last Planck release how important is the polarization. But what I'm saying that in terms of time scale, especially for primaries, now the next step, it's the ball is on the court of larger scale structure. So what happened with this avalanche of data that we have seen lately, since there have been this huge effort to observe as much as you can observe? Well, if I had to summarize everything into a very short sentence, is a wonderful agreement with the standard Lambda CDM model, which somebody called it the maximally boring universe, actually, because, you know, after the model was proposed some 20 years ago, basically it has been unchanged despite of all the effort. With some exception or some tension that maybe we want to discuss later. Yesterday we heard about the H0 tension. There is also the sigma 8 tension that maybe, you know, will be mentioned eventually, but these are there. And so now, if we think about larger scale structure, I've stolen this slide from Dave Schlegel, which redshift we are increasing of a factor of 10 about every 10 years. And you know, if you extrapolate, all linear modes will be mapped by 2043, and all detectable galaxies will be mapped by 2051. And that's some Moore's law for galaxy redshift surveys. So what's the upshot of this? The upshot of this, and what we keep selling our funding agency, is that we can now do precision tests of fundamental physics with cosmological data. Now, the way this game is usually played is that you assume a reference model, which is the standard vanilla Lambda CDM model, and then hunt for departure from it. The same way that people are doing in particle physics, they have the standard model, and then they hunt for it for things beyond the standard model. So you could talk about this BS and beyond the standard model also for cosmology. And the name of the game is that because of the nature of cosmology, the fact that you know, very small scale, by inflation blown up on very large scales, and because we can use the entire universe as a detector, we can really learn about fundamental physics by looking up at the sky, and the information is sometimes very complementary to what can be done with typical ground-based physics experiments. And you know, the two first examples that come to mind is natural dark energy, properties of neutrinos, etc., etc. But so if what we do in our field has implication beyond our field, we need that those implications get believed by people that are outside our field. One thing is to actually, you know, make us ourselves believe the results. Yeah, omega matter, it's, you know, 0.3 or so. And the other thing is that to make this number be believable outside your own community. So if you ever given a talk in front of a particle physicist, you know what I mean by this. So we have you have to pay attention and speak their same language. So what does it mean, speak their same language? You have to be able to convince them that the standard that you've used is also the standard of their field. It's not just the standard of your field, in order for them to believe that. So I'll go back to this a little bit later on, but let me talk about the challenges. So as the statistical error shrinks, because we see more and better, then the systematic errors must be kept under exquisite control. If the statistical errors are of the order of 10–20%, then you know, a lot of systematic error get buried under that. But the moment when the statistical error starts shrinking at the 1 or below % level, then the systematic error creep up, and they really need to be controlled. And as far as I know, we have really good at dealing with statistical error. This is a theory, or, you know, a principled way of dealing with them that has been developed over many years, but we have no systematic way to deal with systematic errors. And here are some more snakes, going back to the title of the talk. So precision without accuracy means nothing, right? You can get to the wrong conclusion with exquisitely small error bars around them, and it will still mean nothing. So bias is a systematic error, but also getting the wrong error bars is a systematic error. So anything that doesn't have the truth within the error bars is systematic. So are there ideas to deal with that? Well, ideas there are, and I think, you know, many of us and you have been trying to deal with this. So let's get illuminated by some Ramsfeld pearls of wisdom. So systematic errors can be divided in several different classes, in my view, from the more benign to the more nasty. So there are the known unknowns, unknown knowns, and unknown unknowns, and they are graded by how nasty they are. So let's start from the beginning. If we talk about known knowns, I think it's relatively, I'm not saying easy, but there is a principled way to deal with this, and this is what our field has been doing for a while. These are the least dangerous because you can either model and or subtract them out. Let's think about, for example, template subtraction. Example of these are, effect of the window in larger scale structure survey, or effect of the beam in cosmic microwave background, shot noise, or some gravitational nonlinearities. So the cons are that this may add a significant complexity to the analysis, and I'm sure you have seen examples of this, but these not contribute to a fundamental limitation. So eventually they can be modeled and can be put in. Then the next one are known unknowns. So we know the effect. We know more or less how it goes, but we don't know exactly how, or we don't know exactly how much. So examples of this, we have seen an example yesterday, the CMB foregrounds, right? Or non-galactic foregrounds. You know they are there, you more or less know how they go, but not exactly. And so one possible solution is to model them with nuisance parameter and then marginalize over the nuisance parameter with some prior, or some prior you have from extra information or from the theory. By the way, these effects should always include in the forecast, and sometimes they are not. And as the statistical error bars really shrink, then it's important to put those in, and this is not always done. Another thing that we've seen about this is the idea of combine suitably the data so they are insensitive to the systematics we are dealing with. And one example we've seen even yesterday is what the WMAP was calling internal linear combination of the various channels. But I learned yesterday that it should actually be called blue. But you get the idea. So this brings me to ask a slightly different question, which brings me to the question of data compression. So we've heard about data compression, but you usually hear about data compression in the sense of I want to maximize the signal. So I want to use optimally my data so that I extract all the signal there is about something I'm interested in. Can I do the opposite? Can I actually compress my data so they are minimally sensitive to the things I don't want to know about because, these are those strange snakes lurking under the concordant cosmology? I mean, it should be possible. It's a similar mathematical approach. It's just you do exactly the dual. So let me show you the approach I took, which it's definitely not the final answer, but it goes some way. And the approach we took was to basically say, well, you have some observable that depend on some interesting quantity and some nuisance quantities. We are ignorant about the mean and the mean values and the error of the nuisance quantities, but we sort of have a clue of how this nuisance quantity goes. And then we just say, can I find a combination of observables that are insensitive to these nuisance parameters? So you can end up writing down a system of equations and then ask yourself, well, go and solve this. And it turns out that the solution really depends on the form of the dependence of your observable on those nuisance parameters. So you have to plug in a form. And so, for example, I plug in a power law. And then if you plug in a power law, you get a solution of a system of differential equation, which gives you a system of linear algebraic equation, right? That then has got a non-trivial solution if you have more data than nuisance parameters, and gives you the combination of data. And you can do similarly for linear dependence. So from this approach, it's obviously follow that you can't do better than marginalization, right? But even with marginalization, you must assume the mean and the errors of the nuisance parameter. So also you need more data than nuisance parameter. I think, with the avalanche of data that we are getting, probably we will be in that regime. If you have fewer observables than nuisance parameters, and this usually happens if the observables are correlated, and this will happen, then exact solutions do not exist, but you can find approximate solutions. And it's a particular case of interest if the observable are similar but not identical dependencies on some of the nuisance parameters, which sometimes may happen. So in this case, it's also possible to write this down mathematically. It may remind you of Lagrange multiplier. I'll just write it down, the equation, but I'm not going to go through the equation. But you get something like this, which solution is quite general and include also the previous case that I showed you before. And by the way, it turns out that if you don't know anything about cross correlations, out of here it will come out that cross correlation are insensitive to systematics, which is a good consistency check that this complicated math speak does what intuitively you would know you have to do. So let me move on and go to the third category, which are unknown knowns. What do I mean? I know that the effect is there, but I don't know enough about it to use option 1 or option 2. So if I know the functional form, then the previous approach will still work. But there are also other cases. So let me give you an example. Galaxy bias. We know galaxy bias is there. We have some hope maybe to model halo bias, but when we go to the galaxy bias, then we are in this category. Or neutrino bias, although on this I want to say a few words in a couple of slides and involve some of the people that are in the audience. And or any other residual from approach 1 and 2 where modeling, it's good but not perfect, and therefore gives you something that looks like this. Also, in here, I put effect of approximations. Let's say adopting an incorrect likelihood. Sometimes we do. Actually, in many large-scale structure survey, for example, for the power spectrum, one takes a Gaussian likelihood for the P of K, which we know are not Gaussian, and with a fixed covariance matrix, which we know should depend on the cosmological model because of cosmic variance. Or incorrect covariance. Covariances are very difficult and numerically heavy to evaluate. I mean, I've seen at least 2 people here that have been really thinking about this, this problem. But just because I can't calculate in a reasonable amount of time, or I may want to resolve to emulators. Emulators are also approximation. If there is any residual left, it will go into this category. And then finally, we come to unknown, where really we really don't know. We may not even know that they are there. And so here we start waving our hands, and we talk about redundancy, which since the statistical power is still real a lot, we can, start, playing around and splitting the data or comparing the data, because you can do with less statistics if you really need to uncover this kind of things, or things like cross-checks. So let me give you a couple of examples coming from work of some students in the group, just to give you some idea of the flavor of things that, that one can do. So the first example I want to give you is something that we call minimally parametric reconstruction with cross-validations. So in here, we took a typical probe of cosmological structures, CMB, CMB lensing, Wiggle Z, and SDSS. The colors are indicated here for the scales, and of course CMB scales cover all the range, and try to do minimally parametric, that is with S-splines, reconstruction of the primordial power spectrum, which, with cross-validation, which means to throw away some data and make sure that when you fit, the fit is actually predictive of the other set of data, so you're not overfitting. And what this shows is the reconstruction of the spectral slope. And the red thing here is what you will get by assuming a power law. So this is the error bar around the power law, and the blue line is this minimally parametric reconstruction. So the data are powerful enough that even if you say, well, you know, I don't assume it's a power law, you still recover something close to a power law. But the interesting thing that we wanted to use this as this sort of consistency check is to say, well, at that point in time, there were a couple of papers out there that were claiming that with non-zero neutrino masses, you would solve, say, the sigma 8 problem. But if neutrinos have a mass of, say, 0.2 eV, then, and you don't know that, when you reconstruct the primordial power spectrum, you should reconstruct a suppression on a small scales to do the neutrino free streaming. And so this method should be flexible enough that if there is that suppression, that fake suppression because you're assuming the wrong model, you should recover it. It's got enough freedom. But the data did not allow you to do that. So this is the reconstruction, and this is what you would expect for 0.2 eV. So this is one possible way to go about consistency check that may uncover, you know, unknown unknowns. And this is another example. So in here, we said, okay, so is dark energy the same in the growth history and the expansion history? Because we know that, you know, dark energy affects both growth history and expansion history. And if it is dark energy and if it is GR, the two are related in an univocous way. And so let me introduce some meta parameter. Let's say I have an omega dark energy for the growth and an omega dark energy for the, for the geometry or the expansion history, and an omega dark energy from the growth. Of course, if everything is consistent, they should be the same thing. And so any constraint should be along the line 1-to-1. And then in here, we actually say, well, why do I have to assume the W is equal to -1? Let's introduce extra meta parameters for the equation of state and for the omegas, and then see what happened. So at that point, we threw in all the data we had, and sure enough, it was offset with respect to the 1-to-1 line. And at that point, we started playing something similar to cross-validation and say, let's throw away the data set 1 by 1, and then 2 by 2, and see what combination send me back, if there is a combination that send me back to the 1-to-1 line. If no combination sent you back to the 1-to-1 line, then maybe you're onto something. But if you pick one data set, and that data set is the one responsible for shifting everything outside the 1-to-1 line, then maybe there's something going on with that particular observable. And so what we concluded here, that clusters were the main culprit for this shift. And we know that the clusters mass observable relation calibration, it's very difficult. So possibly that will be the culprit. So to summarize, here are the problems from the easier to the more nasty. And here are the kind of thing that you can do. You can try to prevent, you can try to uncover, mitigate, or account for them. And so everything that we've done so far and all the ideas we have basically try to move things in different direction, from down here to up here. If you know, the more you know about your enemy, the better you can deal with it. And also to move it in this way. If instead of account for it, you can first prevent or mitigate, it's much better. And of course, any combination in any of this combination of direction. So let me go back to this thing. We can now do precision test of fundamental physics with cosmological data. And the question I have is, what would it take for another community to believe? Imagine we come along and say, we have detected deviation from general relativity, or we have measured the neutrino mass from the sky. What would it take the other community to believe that claim? Which reminds me a lot of credit rating, right? So if you have to invest your money, then you have these various credit rating for countries that tells you, don't invest in Spain, but invest in Germany or things like that, or in France or things like that. This is a similar thing, right? If you want to bet, would you bet BAO, Racial Distortions, CMB, or... What is the set of tests that, if passed, would make a measurement or some measurement convincing beyond our own community? And would we have to specify this set of tests ab initio? Right, before we start analyzing them, we specify the test and we say, if these tests are passed, sorry, you really have to believe whatever comes out. Or can when we ask a posteriori, you say, oh, well, like, the sum of neutrino masses is 0.11 eV plus or minus 0.004. And then can the other one come along and say, no, but sorry, now I'm not convinced you should also do this test. Other communities use a lot blinding, right? Blinding of your data. And in cosmology, some collaboration have started using blinding, but we can't apply it as is from, say, the gravitational wave community, which we know used blinding, and at some point they even went almost to submitting the paper, and it actually, it was a blind signal in there. We can't do that for the nature of the data. And we should maybe want to keep this consideration in mind, because in a second I'm going to bring up again the H0 example. It goes a little bit deeper than that, though. So I like this phrase of Daniel Kahneman about theory. It says we can't live in a state of perpetual doubt, so we make up the best story possible and we leave if this story were true. And in cosmology, we have a lot of stories: GR, Big Bang, choice of metric, nucleosynthesis, and so on and so on and so forth. And also, we tend to rely heavily on models, both for the signal and also for the noise. And all models essentially are wrong. They are models. But some are useful. But with 1% precision, when your model is still useful but somewhat wrong, then that becomes the name of the game. All right, so let me discuss a couple of examples. And the first example is, again, neutrino mass. So we know that cosmology is the key to determine the absolute mass scale. So in this plot, I have the mass of the light's neutrinos and the sum of the neutrino masses. Neutrino oscillation experiments put you in these two thin lines here and here, but you don't know where in these lines. And then cosmology, what has been doing over the year is marching through, putting limits in this direction. The other thing is that this is called inverted hierarchy, and this is called normal hierarchy, and for the generation of neutrino masses, the two hierarchies are important. So in 2015, the CMB Planck plus BAO 95% limit was sitting up here. Now in 2018, with Planck plus lensing plus BAO plus polarization, then this limit came down here. So we are getting in the interesting range, because now it's not that far away from actually you have to see something, because there is a minimum mass down here. And forecast for future survey live here. So this plot means that neutrino contribute at least to 0.5% of the total matter density. But again, when you go below the 1%, then you really have to be careful about this kind of thing. And the other thing is that the Catherine experiment, which probably you've seen because it was in all the newspapers, that's the biggest experiment that we have to actually give us some handle on the neutrino mass, just ground-based, typical physics experiment. Their detection versus 90% limit is up here. Now, this experiment is taking data, hasn't published the results yet. But you see, there's an order of magnitude difference already. And we have results, and they are still taking data. But this is an indirect measurement. What that is more of a direct measurement. Sorry? Right, that's why you have this range, right? Because depending, yeah, exactly. So it's again somewhat model dependent, but we're much more model dependent than they are. Yeah. So by the way, if you add the H naught constraint in, which is not really consistent, then the limits come at 0.1 eV already. But let's leave that. So what does the physical effect of neutrino mass? I think we all know. I don't need to go through that. At neutrino-free streams, and therefore suppress the matter power spectrum on scales smaller than the free stream in length. So in linear theory, you see this is the effect. You show a similar plot before when we were trying to do the minimally parametric reconstruction. But there is another effect here, which we'll see if you zoom in down here. Different masses become non-relativistic at slightly different times. So in principle, cosmology can yield some information about the neutrino mass hierarchy. It turns out it's not exactly the hierarchy, it's the mass splitting, but that's already interesting enough. Now, this plot is true if you keep fixed omega matter h square, omega baryon h square, and lambda. But if you have a CMB prior, these are not exactly the direction of the CMB degeneracy. The direction of the CMB degeneracies are slightly different. So you play with H, and actually you keep fixed now omega cold H square, omega baryon H square, and the angular size distance to the last scattering surface. And then what in the previous plot are now the dotted line, then you get something like this. So you see that other effects come in now. You have effects on the baryonic acoustic oscillation, and I think you see much better this effect on larger scales of that. So let's zoom in, and what this is telling you, if you find a suitable parametrization for this mass splitting, is that depending on if you keep the sum of the masses fixed and then you change this mass splitting, not necessarily in agreement with what neutrino oscillation tells you, then this is the response of the matter power spectrum. But now you can inbuild a consistency check, because if you measure the sum of the masses, then you go to the neutrino oscillation, they tell you what this big delta should be, and then you should go to the larger scale and see an effect that is compatible with that delta. If what you see in small scales is not neutrinos, is something else, then chances are that when you go to larger scales, you're not going to find a signature that corresponds to the same mass splitting. So this offers a powerful consistency check, and consistency checks are good. So that's one way of actually going after unknown unknowns. The other example I want to bring up is, again, the trouble with H naught. So we had the talk yesterday. I don't have to go through the background. Let me just say, so this is the Rees measurement from 2016. And these are cosmic microwave background measurement for the lambda CDM model. This is if you relax the lambda CDM model and you also allow the number of effective neutrino species to vary. And these in green are from the time delay lengthening distances. So what I want to see here is that this is an end-to-end test of the universe. You're trying to thread a needle from one side of the universe, a redshift, a recombination, to the other side of the universe, which is basically a redshift about 0. And did we thread that needle? Well, at the 3.8 to 4 sigma level, depending on which of the latest H naught determination from Adam's group and collaboration you get. So this is my pictorial representation of the cosmic distance ladder. So what we are doing now is we are doing a cosmic distance ladder that traditionally was only getting to nearby supernova. We can bring that cosmic distance ladder all the way to the cosmic microwave background. So how is this done? So lately, in the past, say, 5 years or so, the supernova statistical power and the BAO statistical power have become strong enough that they not just overlap in redshift, but the error bar are small enough that you can calibrate one to another. So the supernova gives you a cosmic distance ladder that is fundamentally not calibrated, because you don't know what the intrinsic supernova luminosity is. You know they're all the same, or they're standardizable, but you don't know how much it is. So you need to calibrate typically on H0. That's what you basically do with supernova. The BAO also gives you a standard ruler. You don't know the length of the ruler from the larger scale structure alone, but the cosmic microwave background tells you what the size of the ruler is, given a model for the early universe physics. But now you can tie these two, so you can do the direct distance ladder, go on. Okay. Let me do that. You can do a direct cosmic distance ladder one way and an inverse cosmic distance ladder the other way. So this gives you the low redshift anchor, and this gives you an high redshift anchor. So good ladders need to good anchor points, and the point is here is that that's where the whole thing fails. So what do I mean by that? So with Jose, a student in Barcelona, we said, well, what about if we leave freedom to the expansion history of the universe and try to let the data reconstruct the expansion history of the universe, and we did it in splines, and see where we end up? Can we explain this mismatch by something with the expansion history? So that's his reconstruction, taking you first one data set at a time and then combining them. And so the upshot is that the shape of the expansion history is well constrained, right? It's a question of mismatch of the ladder. So let me move on and steal a slide from Adam Rees' talk this summer in Cambridge. And what it does, it put up their latest measurement of H0, but it does an interesting split. It puts here the measurement that depend on the early universe, and it puts here measurements that depend on the late universe, and he says, oh, look, they cluster. So in a nutshell, from my point of view, the H0 problem is an anchor problem. You can put the problem at redshift 0, or you can put the problem at redshift 1100, but you can't really solve the problem by messing around with things in the middle. So keep this in mind if you want to search for new physics, or if you want to search for systematics. A delta and effective of 0.4 will do, but if we were no Planck polarization, if with Planck polarization, then this solution makes basically everybody unhappy rather than everybody happy. So let me mention just one last thing, which is what the next generation survey will open up for us, which is ultra large scales. These are scales that above Ka equality, and these scales are a treasure trove for yet undetected effect, but that we know they are there. First, the consistency check of neutrinos, it's also on this kind of scales, but also what goes under the name of GR effects, and also non-Gaussianities. They are all on these very large scales. And you can't do one without the other one, because there can be degeneracies if you just model one effect and neglect the other one. You have to model all of them at the same time. Now, Ben Carlos here has worked a lot on systematics, both 3 different kinds that we've seen on those scales. And there are probably unknown there that we still can't deal with. But what I'm saying is that the current tools that we have are probably not sufficient to actually make justice to these very large scales. You definitely can't do a Gaussian likelihood of P of K there. So for a Gaussian field, you can write what's the P of the multivariate delta there. If for local non-Gaussianity, well, I can even write it down, but I'm sure you don't want to see it. And finally, another question, food for thought, it's experimenter's bias. I mentioned it before. The traditional way to protect yourself against this is blinding, which has not really been very ubiquitous in cosmology. And we have done mock challenges. We have done don't compare with theory. We have done don't plot axis label when you plot the confidence. Weak lenses has perfected this, actually. So in weak lensing, different collaboration have gone through this. but I'm not sure that the same approach can be used to other probe of larger scale structure just for the nature of the observation and the nature on how you compute the error bars around those observations. It has been not done extensively in CMB, although there are some examples, especially for polarization, and not in galaxy surveys. So the other thing that we may want to keep in the back of our mind is some trade-off. So define robust statistics. Optimal, it's probably not necessarily the best. It's not the smallest statistical error bar. A typical example of this, which we were doing blindly more than 10 years ago, it's BAO, right? You have this wonderful power of this galaxy survey that have a lot of information there, and then you go and you do something to your data, and you fit your data with this template and this alpha shift, which is the way you feed the baryonic acoustic oscillation, that throws away a lot of information, but it throws away a lot of systematics as well. And then you end up with a measurement that is much more robust than other type of measurement that has been done in larger scale structure. And that's, you know, one route that makes particle physicists and theoretical physicists to believe CMB, to believe baryonic oscillation, BAO, and then everything else they go, I don't trust it. It's because they use a robust statistic. And somehow, unconsciously, this message went through. So in summary, as the statistical errors shrink, these offer exciting opportunities, ladder, but also challenges, snakes. Systematic error, snakes, are the name of the game here. We need to think also about theory systematics because the measurements are strongly model dependent. I give you a galaxy survey, the first thing people do is transform array and deck and redshift into distances, assuming a model. There is possible a trade-off for precision, for accuracy, and optimal versus robust approaches. And I leave you with this famous saying from the business world that probably applies here too. Thank you.